All right, let's get started. I guess people will trickle in while they're studying for their dynamics exam or what have you. But that's what, the notes on YouTube are for, so if anybody misses anything, they can sort of, catch up. All right, let me start off. I'll get the sign-in sheet passed around, and then we'll go ahead and get into this. Just a little bit of housekeeping. So you all have a present due to me on Tuesday, right? So has anybody looked at it? Does anybody have any questions? Anything at all?
Yeah, we looked at it. We kind of struggled. So we'll probably be in your office sometime. I don't know. Probably tomorrow.
Okay. All right. What I'm probably going to do for your next homework assignment is I'm probably going to give it to you on Tuesday, but in the interest of fairness, I'm going to make it due the Thursday after spring break. So that you all have time to do it. But I'm not trying to be that guy say, oh, I'm going to load this assignment down, but there are going to be a few things on the assignment. There's going to be some Mohr circle stuff, and there's going to be some stuff with combined loading. But we'll have a fair amount of time to go through a lot of this. We're going to talk about Mohr circle today, and we will, I think this will actually be depending on how this goes, this will be a fairly short topic considering all we talked about last time. Last time we talked about stress transformation, and really Mohr circle is just an extension and a simplification, if you will, of all the stuff that we did last time. And then we're going to take Mohr circle and apply it to some fundamental situations that we deal with in engineering. So let me actually pull this up a little, and we'll go ahead and get started. So let me go back a little bit to right here. Okay, so what we talked about last time was the idea of orientation. So, this entire time when we've been cutting sections, we've been cutting them perpendicularly, So the idea behind what we were talking about this time is, well, what if we cut them at an angle? Sort of cut it like this, like a ninja chop, something like that. Yeah. We've been doing judo chops the whole time. Now it's time to do ninja chops, right? Now don't go karate chopping while you're kung fu kicking, because you go like that, there goes your leg. We got some folks who get the reference, and I'm happy about that. So this whole time we've been judo chopping, and now it's time to do some ninja chopping. And when we do in all seriousness into the mechanics, when we cut at an angle, we recognize that we're going to be developing stresses that are different. Okay, if I go back a little bit and we say, all right, if I have a single stress and I apply it axially, if I cut perpendicularly, it's just the same stress. It's just static. Sum of forces in the x direction must equal 0. But if I cut at an angle, I get different components. Okay, I get a normal stress and a shear stress. And if I do the same thing for all the other potential stresses, the idea is that if I have a stress state that is defined with respect to just a random coordinate system, and I want a stress state with respect to another coordinate system, then summing everything up and doing all the algebra and keeping everything tidy, I get this. So this is sort of a nutshell, a hey, here it is, that will transform stress state 1 into stress state 2 depending upon a change of orientation. And I'm going to pull this up real quick just to sort of make sure everybody's understanding the graphics of everything. So we looked at this video last time, and this is just showing a stress element and a given stress state. And you see that as your angle of orientation changes, the resulting stresses on the face of that stress element change as well. Okay? And what we were after last time was really two things. Number one, given stress state A, how do we determine stress state B given an angle, which all in all, it really is just, plug and chug. It's pretty straightforward. There's not a whole lot to it. The second thing we wanted to ask is, well, what's going on here? Okay, and this is a really, nifty orientation because two things are happening right here. We have an orientation where there's no shear stress. That's point one. And then we have an orientation where our normal stresses are maximums. Okay, we have the largest possible maximum stresses as well. Now, likewise, we have a situation, like right here where we have maximum shear stress, and these two are equal and opposite, or equal stresses as well. We'll get into that today. How do we determine those principal stresses? Well, we're talking about maximums, so that's derivatives. So since our stresses change as a function of our orientation, really what we want to determine is the principal orientation. So if we take the derivative with respect to theta and set that equal to 0, we can determine theta sub p, our principal orientation. Okay? And then take that theta, plug it into, this, go through and grunt it out, plug and chug, and, go through and do all the alphabet soup, and we get this. A sigma sub 1 and a sigma sub 2. So this is principal stress 1 and principal stress 2. The difference is, principal stress 1 we can say is addition here, and principal stress 2 is subtraction. And then we did this example based on that same stress state we were looking at earlier. Can we determine the principal stresses and the principal orientation? Pretty straightforward, right? One of the nice things about this methodology or this formulation is that given a stress state, you actually don't need to determine the angle to determine principal stresses. You can literally just plug and chug, and it's pretty nice. Sound good? Now, we've seen a whole lot of, let me sort of blow this up. We've seen a whole lot of sines and cosines popping up in this derivation. And I don't know if you remember, but sines and cosines are very heavily related to the geometric properties of a circle, okay? Specifically, sines and cosines are your x and y coordinates on a unit circle. That's what they are. So the nice thing about this this formulation is that we can take all of these complex equations and develop a graphical approach that will essentially give us all the answers that we need for a stress or for a given stress state. Not only will it tell us the principal stresses, not only will it tell us the maximum shear stress, but it will tell us the stresses at any orientation. All we got to do is calculate the coordinates on the circle. It's pretty straightforward. All right, so this relationship for a stress state, this circular relationship, has a very special name. It's called Mohr's circle because Otto Mohr developed it and he got to name it after himself. All right, so here's the idea about how this works, okay? In that box is the fundamental equation for a circle. So if I had to guess, if you took pre-calculus here at Marshall, you probably discussed that. Is that where you would have talked about that? You did. Okay. All right. So x minus h squared plus y minus k squared equals r squared. R being the radius of that circle, and h comma k being the coordinates of where the center of that circle is. I'm assuming everybody in here is familiar with that terminology. Might have been a while, but you've at least seen it before, right? Okay. Now, what I'm going to do is take these relationships for a normal stress and a shear stress. I'm just dealing with sigma 1 for now. It really doesn't matter, and you'll see that here in a second when we look at the properties for the circle. But sigma 1 and tau 1, 2, I can rearrange those a little bit by moving some quantities over to the other side. And then what I'm going to do is square them. Okay, now first off, why am I squaring them? Well, I'm squaring them because of this instance right here, x minus h squared and y minus k squared. Now, if I'm squaring this, that means I'm squaring that, which means I got to do a little bit of foiling, right? First, outside, inside, last. So if you go through and grunt all of that out, you can follow along. So, first times first, outside times outside, inside times inside, and last times last, go through and chug that out. This is the sigma 1 squared, and this is the tau 1, 2. So go through and chug it out. Add those two terms add those two terms together, and what's happening is this. You'll find that a significant component of it is going to cancel, and if you look at like terms, for instance, if I add these two up, I'm going to have this times what? Sine squared plus cosine squared? And what is sine squared plus cosine squared? 1. So a lot of this trig gets washed out. Okay? Make sense? All right. So while this got nasty for a little while, it actually gets simple when you start looking at the formulation, and it gets simple real quick. Okay? So this right here is the equation of a circle. Okay? So let me go back. All right? So x minus h squared plus y minus k squared equals r squared. Okay? So what's going on? Okay? This is the equation of a circle. So here we go. I propose that we calculate two quantities. We calculate average stress, which is just sigma x plus sigma y over 2, and we calculate r, which is the radius. Okay? Now, the nice thing about this is look at this sigma average plus r. Look at this and look at this. Okay? Here's where the speciality of this relationship comes into play. Have we seen these expressions before? Well, look at this. Let's go back to principal stresses. Look at that. The principal stresses are this plus or minus that. Or the average stress plus or minus the radius of Mohr's circle. Does that make sense? Let's go here. All right. So here's the long and short of it. When we plot Mohr's circle, we're going to do this. We're going to calculate the average stress as follows. We're going to calculate the radius, and we just plot the circle. The circle will lie along the x-axis. Whatever sigma average is where the average stress is, and r is the radius, and there you go. And that's it. We're going to see some really nifty corollaries with this as we get into the math. But let's plot Mohr's circle for this and see what it looks like. All right. Okay. Okay. So now we are still dealing with the same stress state that we were before. Okay. So just so everybody's clear, we're still dealing with a sigma x of what? Plus 6 ksi, a sigma y of minus 10 ksi, and tau xy of, what was it, minus 5? All right. So using these quantities, I want to calculate the following. The first thing I want to calculate is sigma average, which is just sigma x plus sigma y over 2. So what does that come out to be? Or 2 ksi, right? Now, if you want, you can think of it like this. This quantity right here is the center of the circle. That's where the center is. All right. Oh, sorry. Whoops. It does matter. Yes, it does. What? I'll just conveniently ignore that. It's still mistake number 4. All right. Okay, now what's r? R is, let's see, the square root of, okay, sigma x minus sigma y over 2 squared plus tau xy squared equals 6 plus 10 over 2 squared plus minus 5 squared. So what does this come out to be? He's making us do math. Oh my goodness. Square root of 89? So what is the square root of 89? It's not a pretty number or an integer or anything like that. Like that? All right. All right. And keep in mind this is the radius. All right. Sound good? All right. Because I think it's important, at least for the sake of the video and what's on the screen, to try and draw this exactly, I'm going to see what I can do. All right, give me a second. So, has everybody got this? Okay. I don't usually use these little tools very much, but I think I kind of need to here. All right. So, okay. How does, oh, that's not correct. Nope. Supposed to be like that. All right. There's like these little tools here I want to try and use. Okay. All right, let's try this. Oh, nope. There's that. There's that. So now it's perfectly straight. Okay. Now where's the little circle thing? Nope. Nope. There we go. Okay. Now let me see how this works. Okay, yep, there we go. Okay. All right. Let's see, let's do this. Let's make the line, I don't know, red. Okay. All right. So here's how this works, okay? You start off and you locate your center, which is going to be somewhere about right here, and then you draw your circles. So let's see. It's going to be about right there. Oh. Oh. There we go. All right. Now let's try this. Probably something about like that. Okay. Now, let's see if I can take this and, I don't know, maybe move it over a little bit. Something about like that. Make it red or something. There we go. Okay. Everybody okay with this? All right. Now let's actually just do some general writing. So, okay. All right. So, let's label some things and make sure we're all clear with what we're looking at. Okay, so here's a plot of a circle. Okay, now on this x-axis, this is going to be my normal stress. And if you want, you can call this sigma 1. Okay, sigma 1. All right, on the y-axis is our shear stress, or tau 1, 2. Okay? All right. Now, first off, the center. Okay? Now, I'm proposing that the center of this circle is somewhere about here. Okay, now that's the center of the circle. Is everybody okay with that? Can everybody see that? Everybody okay with that? Okay. Now, I propose that the coordinates of that point, the x and y coordinates, are -2, 0. Everybody okay with that? Actually, let me put that down here. I'm going to need that space. Okay. Everybody all right with this? Now, what is the radius of this circle? What is that distance right there? And actually, you know what? Let me just leave the units off since I've got the axes labeled. Everybody okay with this? What do you mean? Because that's a good question. Because of that. -2. I'm placing it on the x-axis. I'm saying that for Mohr circle, the y-coordinate is always going to be 0. Did I answer your question? Okay, that's important because I want to make sure that you get that. It's always on the x-axis. It's just, why is it always on the x-axis? Okay. The reason why is because if you follow the derivation, what ends up happening is, remember this is your equation for the coordinates of a circle? If you go through and chug everything out, you find that you don't have a term right here. So this is like x minus h squared plus y minus k squared, but there's no k, so k is always 0. Does that make sense? That's an important question, and I want to make sure everybody gets that. You good? What about everybody else? Am I good? Okay. All right. Okay. Now, here's the points I want to make. Okay, help me out. How do I determine the coordinates of that point? Help me out. How would I determine the coordinates of that point? Add the radius, right? What is that? Help me out with that. 7.434, comma 0. Is everybody okay with that? Now, help me out with this. What then would the coordinates of that point be? Make sense? Is everybody okay with that? Now, I want to go back to this. What did we do in example 28b? Determine the principal stresses. What did we get in that example for our principal stresses? All right, I propose to you that the x-intercepts for Mohr circle will always be your principal stresses. This point will always be sigma 1 and sigma 2. That will always be the case. Make sense? And if you don't believe me, look at this. Look at the formula for sigma 1 and sigma 2. Well, actually, I got them backwards, but that doesn't really matter because as long as you've got the magnitudes, that's all you really care about. This is center plus radius, center minus radius, right? Sound good? All right. So, if you want to be a purist, no, I do. That's fine. If you want to be a purist, you can say that that's sigma 1 and that's sigma 2. But it doesn't really matter. All you need is the magnitudes. Because as an engineer, all you want is that worst case scenario to compare against a factor of safety. All right. Everybody okay with this? Now help me out. For this stress state, if this circle represents what the stresses are at any random orientation, what is the maximum shear stress? And what is the value there at the top of the circle? What is the maximum shear stress? In other words, if shear stress is on the y-axis, it's just going to be the radius, right? So I propose that here's the deal, okay? What are our worst case normal stresses? Sigma 1 is 7.434 KSI. Sigma 2 is minus 11.434 KSI. And tau max, which is right here, That's tau max. Tau max is just the radius, which is 9.434 KSI. Oh, it's going to get better. It's going to get much better. You're going to like this. Watch this. Y'all dig through your notes a little bit, and I want you to tell me what, let's put this down below. Note. What was theta sub p? What was the principal orientation? Let's deal with the negative angle. Right? All right, now help me out with this. Let's do this. What's 2 theta? What? 32.006. Is everybody okay with that? Okay. Let's check this out. Why am I doing 2 theta? Because if you remember, look at all the sines and cosines in our stress transformation calculation. They're all 2 thetas, right? Watch this. Now, a negative angle starts at the x-axis and goes down, right? Right? Remember, if you're rotating, this is 0, this is pi over 2, pi, 3 pi. This would be negative pi over 2 and negative pi. Y'all remember that? All right. So would you agree that 2 theta is probably going to look something about like this? Something about like that? Right? So this is what? 32.006 degrees? Everybody okay with that? What I want to know is what are the x and y coordinates right there. So how do I do that? Let me scroll down a little bit. Would you agree that I could idealize that as a triangle that looks something like this? And what is this? Is 9.434. This is 32.006 degrees, right? So, can you all do the trig and tell me what are the x and y lengths of this triangle? Let's start off with y. Remember, the sine of that angle is going to be y over 9.434. So that's going to be 9.434 sine of 32.006 degrees. And what does that come out to be? Maybe like minus 5? Or maybe 5. Let's do 5. No. Let's do 5. 5. Everybody okay with that? All right. Now, x equals 9.4. I can do better on that now. 434 cosine of 32.006. What does that come out to be? 8. I promise if you go through and track all your decimals and all that, it comes out to be exactly 8. And this comes out to be exactly 5. Watch this. The height of this is 5, right? So would you agree that if we're looking at this coordinate system and we're trying to determine x, y coordinates, that that's going to be minus 5 because it goes down? Everybody okay with that? Now, if the distance from the center to right there so if this is 8 from here to here, what are the coordinates of that point? 6. Interesting. So help me out with this. let's do this. What then are the coordinates of that point? First off, the y coordinate. What's the y coordinate? Say it again. 5. What is the x coordinate? Negative 10? Is that what you said? So we've got, hold on. Let's see if we understand this. So you're telling me, I'm going to go back a panel. You're telling me we've got 6 comma minus 5 and that. Now, just take a breath. It'll be all right. Craziness, right? Mohr's circle is constructed based off of your principal orientation. Honestly, that 6, that negative 10, that negative 5, that was arbitrary. Those are just the values that we got putting our x and y axes on our beam or column or shaft or pressure vessel or what have you. We just put those coordinate axes where they made sense. The values that really matter are principal stresses and maximum shears. If we turn that principal orientation, it's funny how we get back to right where we started. So your x coordinates will correspond to your normal stresses, and your y coordinates will correspond to your shear. Now, shear's positive shear and negative shear, and honestly, from a design standpoint, it really doesn't matter. If I take a member and I go like that versus I take a member and I go like that, I'm doing the same thing to it. It's just a matter of flipping it around. So it's the same thing. Now, normal stresses, that does matter, because whether I take a member and yank on it versus taking a member and compressing on it, you can get different behavior. Things in compression like to do this little thing called buckling, which we'll talk about near the end. All right. What do you think? Nifty stuff, right? Well, as long as you're keeping track of your signs, yes, you are right. But that's sort of where, like if you've got a beam that has multiple point loads on it, right? Okay, each one of those point loads are going to generate different shear stresses, or different shears. But that's where a shear diagram comes into play. When you draw a shear diagram, you are taking into account your sign conventions, because you're either going up or going down. But when you're in design mode, you just look at that shear diagram and say, okay, what's the worst case magnitude? And that's the one you're going to use for design. Whether or not that magnitude is a positive 2,000 pounds or a negative 4,000 pounds, you're just going to go with the 4,000, because magnitude doesn't matter. In that instance, we're talking about either doing that or doing that, and it doesn't matter. Make sense? Any questions?
The only reason we double the theta is because we do theta every single time in a formula.
That's why, yes. Because when you go through and do the math, you find that your stress rotations, or your new stress state, is really a function of 2 theta and not theta. And that's how Mohr's circle is being developed. In other words, if I take a stress state and I actually rotate it 180 degrees, it doesn't change. That's why when we did that last example and we said, all right, the principal angle was negative what? Negative 116, or no, not 116. It was negative 16.003. Isn't that what we got? Okay, we could do negative 16.003, or we could do, what was it, 100? 163. So what I was basically saying was, you can get the same result by either turning 2 theta this way or turning that way. It's the same thing. So I think it's easier dealing with the smaller numbers. So that's just me. But if you don't like negative angles, that's why we did that. But that's why we added 180 and not 360. What do you think? It is a pretty cool looking circle, if I do say so myself. All right. Any more questions? Okay, now what we're going to do now is we're going to employ some of this stuff a little bit. In other words, you know, I think it's, here, let me go to here. Okay, yeah, here's where I want to go. Okay, I think that all in all, this is a pretty nifty example, but it's based on some arbitrary numbers, you know, 6 KSI, a negative 10 KSI, or 5, what have you. I think we need to tie this to some real stuff that not only you've already seen, but stuff that you will see in your career. You know, take a beam. A beam experiences shears and moments. So it experiences shear stress and normal stress. Okay? So we need to understand worst case scenarios in very common instances. Okay? Now, the only thing I will point out is this. Okay? Mohr's circle can be used for a number of different applications other than stress. You can also draw Mohr's circle for strains. You know, a strain in the x direction, a strain in the y direction, a shear strain. Okay? The only quirk to it is that when you're dealing with shear strains, you have to divide by 2. And I don't want to go into the math. There's a lot of, you know, intricacies into the math as to why why you're dividing that by 2. But the long and short of it is this. When you look at a two-dimensional element and it deforms in shear, you're basically changing the angle. But because of that, you can change the angle with respect to the x-axis and the angle with respect to the y-axis. So there's sort of a doubling effect with strain, and that's why we divide by 1/2. Honestly, for the purposes of what we're talking about, you know, just sort of plug in the half and go with it. If you want to follow along with the derivation, there's a pretty detailed one in the book, but I don't think it's important enough to go through every nitpicky little step for this in here. What I was more interested in is that you could get to here, okay? And if you understand that, then 90% of the work is done. I just don't think it's worth discussing. It's really intricate, and all in all, what you're going to take away from it is just divided by 2. So I know how things go. All right, everybody okay? Now, one other application is you can actually use Mohr's circle to determine the optimum orientation for a given beam. Now, if you're dealing with like an I-beam or a rectangular beam or something like that, it's pretty simple. It goes like that. But if you've got a beam that has a really funky cross-section, which stuff like that happens. I mean, what do you think a wing is in an airplane? You know, do a samurai sword or lightsaber through a wing, and that's a beam with a really funky cross-section, you know. So determining its optimum orientation, that's actually worth some discussion, okay? And you can use Mohr's circle to do the same thing, to determine the optimum orientation in the x direction or the y direction, or in this case the 1 and 2 direction. The only difference is with your product of inertias, you have some sign changes. And again, it all goes that goes to sign conventions, and it's pretty straightforward, but again, it's not worth the detailed discussion for what we're talking about. As long as you understand the 4 fundamentals of Mohr's circle, I'm happy. Everybody good? Okay. Now let's start applying Mohr's circle to some real-life situations. And I want to start off with combined loading. Now, by combined loading, what I mean is this, okay? So our big 4 stress formulas, the 4 fundamental stress formulas that we've spent the last, 10 weeks, 9 weeks, 10 weeks, or the first 9, 10 weeks of the semester deriving. The fundamental stress formula for axial stress, P over A. The fundamental stress formula for bending, My over I. For shear, VQ over IB. And for torsion, TR over J. That should be very familiar given the stuff we've talked about this semester. Everybody's okay with that, right? Now, what you all know how to do is properly assess the conditions for each one of those, okay? If I take a bar and yank on it, you can tell me how much it elongates, you can tell me the stress, you can tell me whether or not it's sufficient or not. If I give you an allowable axial stress, you all can do that. That's simple. But what if I took that bar and I yanked on it and I twisted it? Now, it's not so simple to determine whether or not it's good or not. Okay? Now, even if I give you an allowable axial stress and an allowable shear stress, you still can't theoretically determine whether or not it's safe because you've got multiple stresses acting at once. And at least from the Mohr circle discussions that we've had and the principal stress discussions that we've had, you know that if I just give you some stresses, that under a given orientation, those stresses can get worse. You know, we went from 6 and 10 KSI to like 7 and 11 KSI. You know, the stress is bumped up. Maybe not a lot, but in some conditions, they could really bump up. You see what I mean? So you have to understand that worst case orientation. Okay? Now, one very common example is this, a beam. Okay? Now, before we, you know, draw this beam and start doing calculations and start getting into it, let's just conceptualize this a little bit. Okay? Let's make sure we're understanding the approach and what this problem's asking for. So I have a beam. It's simply supported. It's subjected to a point load about 2 foot from that right support, and it's, what, 10,800 pounds? So what I'm going to do is draw the shear and moment diagram for this. So I'll have to compute reactions, draw shear diagram, draw a moment diagram, all that. So I'll be able to determine a maximum shear, or I'll be able to determine shear at a given point, and I'll be able to determine moment at a given point. That's, I think, pretty simple. Okay, everybody okay with that? Now, what I'm going to do is identify a given point on the cross section. Essentially, we're going to look about right here, 2 inches from the top, about right there. Okay. Now, at this particular point, right there, we're going to have a bending stress, and we're going to have a shear stress. Now, we're going to determine those bending stresses and shear stresses while we're going to use our just basic fundamental equations. We're making the assumption that this x and y axis is the axis that matters. Okay? But we know that might not be the case. Maybe it's this axis that matters, or that axis that matters, or this axis that matters, right? So we're going to determine stresses at that point, and then we're going to rotate it using Mohr circle and get the worst case scenario. Everybody okay with that? So let's take our time with this one and make sure we understand what's going on. Everybody good? All right. Okay. Okay. So before we get into stresses and all that stuff, let's just do our support reaction, shear and moment, all that. Okay. I'll call this structural analysis. All right. So what do we got? We've got a load going something like this. What's that? 10,800 pounds. That is 2 feet. This is, well, here, actually, no, let me do something else. Let me do this. Let me not be lazy with it. Okay, so I'm going to have some unknown reaction here and some unknown reaction here. Now this dimension is 4 feet, and that's 2 feet. Okay. Reason why I put those down below is because I wanted to draw this. That's ultimately where we're going to need our stresses. Now this was 9 inches. Is that what it said? So 0.75 feet. from there, right? 9 over 12. Did I do that right? All right. So this is AY, BY. Okay. You tell me what to do. What do I do? No. For this, we will assume that the beam is sufficiently weightless or the weight is so light that it doesn't matter. All right, so let's sum moments at A. I can do better than that. All right, so you tell me what to write if I'm summing moments at A. Does AY cause any moment? No. Does the 10,800 pounds cause a moment? Okay, does it belong on the left side of the table or the right side of the table? Left side. And what's the moment arm? Okay. Everybody okay with that? Now, next one, we've got BY. It's got to resist that. Moment arm of what? All right. So on the right, BY times 6 feet. What is that? 43200? I did that in my head. I've got the answer right here, but I'm not looking at it. Is that right? All right, so divide by 6. What does that come out to be? Comes out positive, no need for significant emotional distress. Sound good, right? What's next? I mean, we're going to take this one, one step at a time. Some forces in the y direction. What do we got? AY going up. We got, and that is 7,200. And we've got what does that come out to be? There we go, 3,600. Sound good? All right. Now, all right. What do we do? So first thing we do is draw our shear diagram. This is going to be a shear diagram in pounds. That's what we do. We go up 3,600, right? No change. Go down. No change. Go up. So 3,600. Bless you. Go down. No. We don't go down to negative 3,600. AY pushes up to 3,600, and then if we go down 10,800, that puts me at negative 72. Make sense? Yeah, this, keep in mind, this BY is 7,200. This is 3,600. Everybody okay with that? Areas. What's the area under the curves? 3,600 times 4, right? Big number. What about this one? 7,200 times 2? There you go. Good, right? We want those to be equal. Oh, no. Let me drop this down a little bit. So how do I draw the moment diagram? What's it look like from here to here? Some straight line, yep. And from here to here, another straight line. So, moment diagram goes up and goes back down. Any questions? Now, let's remember, our eye needs to remain fixed on that section, okay? So, let's go back up here. What is the shear at that section? Remember, we're looking right here at that dashed line that's 0.75 feet away from A. So what's the shear right there? 3,600. So we'll say at section, and I'll call this MN because that's what it was called in the problem. This is M and that's N. The shear is 3,600 pounds. Now, the moment, we're going to have to drag that down. The moment, what we're looking for, somewhere about right there, right? Now, you can do this any number of ways, right? What you could do is this. For the moment, you could say, well, 14,400 foot-pounds is to 4 feet, and ask yourself, well, what is that moment with respect to 0.75 feet? Just linear interpolation. You see how I did that? Or you could cut a section and just say it's 3,600 times 0.75, however you want to do it. Doesn't matter. You end up getting a moment of 2,700 foot-pounds. Does that make sense? Now, that's foot-pounds. Pop quiz, how do I convert that to inch-pounds? Multiply by 12, not divide by 12. There was a few folks on the exam still doing that. 32,400 inch-pounds. Any questions? Everybody good? All right. Do I need to leave this up here for a second? Okay. Everybody good? All right. All right. So, V was 3,600 pounds and M was 32,400 inch-pounds. All right. Now, let's do some section properties. All right. Help me out. What's the dimensions of this beam? Two by 6? All right. So what's I? There we go. So what's that equal? $36. Sound good? Inches to the fourth, right? Everybody good? All right. Now, let's look at this, okay? Here's that rectangle, right? So this is 2 inches. That's 6 inches. Sound good? Now, let's see. Would that be the neutral axis? Somewhere about like that? Where this distance is what, 3 inches? Why does that matter? Well, what did the problem ask for? 2 inches from the top. So the stresses that we want are right here. That's where we're looking. All right. Sound good? Now, the first thing I want to determine or look at is bending stress. What does bending stress look like? Was it do something like this? Something about like that? Now help me out. That's the neutral axis, right? And right about here, that's the section that we're looking at. So my question to you is, what is y? Sigma equals my over I, right? What's y? One inch, because, hold on, let's remember, sigma equals my over I. Where is y measured from? Not the datum, the centroid. So, y is 1 inch. So therefore, the bending stress, or the axial stress, is my over I, which is 32,400 times 1 inch over 36 inches to the fourth. So what does that equal? 900 what? 900 psi. Any questions? Now, is that the only stress that this section is seeing? It has shear stress. Now, you all remember that formula? What was it? V over what? 2I h squared over 4 minus y naught squared. Y'all remember that? Did I get that right? I'll make you go through and check and see if I got that right. That's right? Okay. Now, why not? From the centroid to where we're evaluating. So that is 1 inch. All right? So we have, what's the shear? Two times 36 inches to the fourth, right? Six inches squared over 4 minus 1 inch squared equals what? Y'all have your calculators. All right, somebody got 400? Is there a second on that? Second. All right. So, let's be clear. At that particular point, we have a bending stress of 900 psi and a shear stress of 400 psi. Does that make sense? Everybody okay with that? All right. If you're okay with that, then here's what I propose. All right, can I go on to the next panel? Now we need to do a Mohr circle analysis. Although instead of drawing the circle, we can just use the formulas. Now, in order to draw a Mohr circle, we need a sigma x, a sigma y, and a tau xy. Okay. Now, what was our shear stress? 400 psi. Now, our bending stress, what was our bending stress? We just did it. 900. Now, pop quiz. Was that bending stress in a compressive nature or a tensile nature? It was compression, right? Remember, it was above the neutral axis, positive bending. That's compression. So I propose one of these normal stresses needs to be a compressive stress of 900 psi. So what I'm going to do is say negative 900 psi. Tensile being positive, compressive being negative. Now those are the only stresses on there. There's just a bending stress and there's a shear stress. So what do you think's going on with sigma y? It's 0. Sound good? Is everybody okay with this? What's that? Because there's nothing else there. Because all I've got, see, here's my structure. It's just a beam with a load on it, right? So I develop a shear force and a bending moment. I'm not taking the beam and pulling it like this. I'm not taking the beam and twisting it or doing anything else. This is all I'm doing to it. So that's all that's there. I mean, think about it. If I didn't have that 10,800 pounds, what would the stress state be on that beam? There'd be nothing there, right? So I'm only filling in values where there are stresses, right? There are no stresses in the y direction. I'm not taking this point. See, the only way to, for a situation like this, the only way to generate stress in the y direction or stress this way would be if I took a big C-clamp and just, clamped it right there, and actually started pushing it. I'm not doing that. Do you see what I mean? I mean, imagine what would happen if I took a C-clamp and just started tightening it right here. What am I going to do? Sandwich that. You see what I mean? I'm not doing that, so 0. Or I could take it and yank on it, I suppose, or something like that. Does that make sense? Everybody okay with this? Now, is everybody okay with the signs? The shear stress, it's not going to matter if it's positive or negative, and you're going to see this here in a second. Everybody okay? Now, I propose we need to calculate two things, a sigma average and an R. What's sigma average? Well, how did you do that? What's the formula? Make sense? Now, what's the radius? Somebody else. Somebody help me out. What's the radius?
Square root.
Or plus, wow, hit equals there. Plus tau xy squared. So, see, if you notice right here, it doesn't really matter if we had a positive shear stress or a negative shear stress, because what am I going to do to that shear stress? I'm going to square it. Doesn't matter. So, equals negative 900 psi over 2 squared plus 400 psi squared equals. What does that give us?
602.0.
So just 602.1. Sound good? All right. So you want to determine principal stresses? Here's how it works. I propose that sigma 1 is sigma average plus R. Sigma 2 is sigma average minus R. So what do those come out to be? And the next one. Now, what's the maximum shear stress? Let's see if y'all are paying attention. What is the maximum shear stress? R. There you go. Which is 602. Now, what if I told you, this is where this is important. First off, here's your answer, by the way. This is your answer. So, now, let's think about this with our noggins. What if I told you that this material had an allowable axial stress of 1,000 psi? Would it be sufficient? Normal stress, axial, normal, of 1,000. Would this be sufficient? No, because this is 1,052, right? Before, we wouldn't have said that. We would have said, oh, it's 900 and it's good, right? You see what I mean? By changing your orientation, the stresses get higher, okay? We're looking for worst case scenario as designers, okay? So while our bending stress formulas and shear stress formulas work nice to give us those individual stresses, when you've got multiple stresses going on, everything changes. This shear stress serves to up this at a different orientation. Okay? I mean, think about, and vice versa. I mean, here's our maximum shear stress, or here's our shear stress according to that orientation, but really the maximum shear stress is 600. You see what I mean? So our coordinate system, that X and Y, that's just to make our lives easier. Really, this is what we got to worry about. Okay? So this is sort of a really fundamental topic in the class, the idea that, okay, I've got this piece, this stress, the axial stress, the torsional stress, the bending stress. I can calculate each one of those individual components, but what about bringing it all together? That's what's going on here. Any questions? Did this make sense? I know you all are probably sitting here thinking, dynamics, 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 dynamics. Oh, what the heck was that? All right, hold on. Before I leave you to deal with stress and post-traumatic stress after your dynamics exam, it was a joke, not a very funny one, probably not now. Let me just sort of recap or give you a taste of things to come. So we're going to do another similar problem where I'm taking a member and I'm yanking on it, I'm twisting it, I'm bending it, and I'm doing all this stuff, and we're going to try and determine principal stresses. So that's going to be point 1. And then we're going to do another combined loading scenario that we haven't seen before. Well, I wanted to hold off until now because it is a combined loading scenario, a situation where you get multiple stresses at the same time. And that's a pressure vessel. So we're talking about a cylindrical shape that has an internal pressure built into it. And this could be valid for whether or not you're a civil engineer, mechanical engineer. This is a very valid consideration. And the idea is that if you put an internal pressure inside this cylindrical shape, not only do you get what are called hoop stresses, stresses along the wall of the thickness, or along the wall of the pressure vessel, but you also get stresses acting like that, along the length of the cylinder. So you actually get a sigma x and a sigma y. So it is a combined loading scenario that you have to be able to assess. So we're going to look at pressure vessels and see what are the maximum stresses there. And the last thing is buckling, and then we're actually starting to run out of stuff to talk about. I might start ramping things up a little bit near the end. I'll add some stuff to have some fun. Last year, that was it. That was what we stopped on, was column buckling. We still got 2 more weeks. I'm going to have to come up with some stuff. What's that? Oh, that's a good time. That's a good time. All right. I will leave you to your dynamics exam. You've enough talk about stress today. You can talk about post-traumatic stress. No, I'm just kidding. I'm really kidding. In all seriousness, good luck on your exam. Remember, sum of moments doesn't equal 0 in there. So.